This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, we are discussing the radiation process in heat transfer. The heat transfer is the study of transmission of thermal energy from higher temperature to lower temperature on account of temperature difference. The rate of heat transfer is directly proportional to the temperature difference between the heat exchanging regions or the bodies. Once the process is incomplete, the heat energy which is stored within the body may be in the form of potential energy, kinetic energy or internal energy. Therefore, the heat transfer between the two regions or the bodies maintained at different temperatures can be transferred by using three modes. One is conduction, convection and radiation process. In conduction and convection modes, the heat flows from higher temperature to lower temperature region or the bodies. But in the case of radiation process, the heat transfer is taking place between the two bodies. That means even though the temperature difference is there, the heat transfer is taking place from the body which is having lower temperature, and the heat transfer is also taking place from higher temperature. But the net heat energy is always transferred from higher temperature to lower temperature of the body. Here the conditions. Here the conduction is the process of heat transfer from a higher temperature region to the lower temperature region within a body or between the regions which are in contact with each other. That means they are in physical contact. So the heat energy is transferred only because of exchange of molecular kinetic energy till the temperature along the entire length of the body becomes uniform or equal, which is shown in figure 1. The heat transfer by the conductions is determined by the thermal conductivity and the temperature. So according to the Fourier's laws of heat conduction, the amount of heat energy that transferred is directly proportional to the temperature difference and thermal conductivity values. Here the equation it can be written as now Qx is equal to minus K into dt by dx, or in other words, the amount of heat energy that is transferring from one region to another region within a body or between the two bodies which are in physical contact is directly proportional to the area of the contact and the temperature difference between the bodies. Since as moving just along the body, when the heat transfer is taking place, the temperature is also decreasing. Hence, the temperature gradient, that is the final temperature to initial temperature, is negative. Hence, this equation can be represented as Qx is equal to minus of Kx, K into A into dt by dx, where K is representing the thermal conductivity of the materials, which is generally expressed in watts per meter per degree Kelvin. A is the cross-sectional area in which direction the heat energy is flowing, and dt by dx is called temperature gradient. That means the change in temperature per the unit length. The heat transfer by convection process is generally it takes place in gases as well as in liquid. So there is no the heat transfer by convection process generally takes place in liquids and gases. It is only due to the temperature difference that is existing between the two regions. So the heat transfer by conductions occur. It is a combined action of heat conduction as well as the mixing of motions. So when here as shown in figure now, the liquid is kept in a vessel or the container. The heat energy is supplied from the bottom of the container. As the heat energy is flowing from the solid body to the liquid body, the liquid which is having in contact with the bottom surfaces get heated and flows in upward directions. So the density will decreases, hence it will move upward directions. The liquid which is just at the upper surface, because of having higher densities, it is moving in downward directions. Hence the heat energy is generally transfer taking place because of density difference between the liquid in different regions. If the process is taking place without aid of any external agent like pump, fan or the blower, then it is called natural or free convection process. But if the convection process is taking place with aid of some external like blower, fan and pump, then the heat transfer is called forced convections. So the heat transfer by convection process is given by Newton's law of cooling. It is expressed as Q is equal to H into AS into TS minus TF, where Q is the amount of heat transferred between the two regions. H is equal to convective heat transfer coefficient, which is expressed in watts per meter square per degree Kelvin, and Ts and Tf is representing the temperature of the surface as well as the fluids respectively. The radiations. The radiation process is taking place between the two bodies or the medium, which are separated by a larger distance and not having any physical contact with each other is called radiation of heat transfer. The radiation heat transfer does not require the presence of any intervening medium. Generally, it takes place most effectively in vacuum. The example, the heat transfer which is taking place, that is the transferring from the sun to the earth, it is the example of radiation process. In thermal radiations, the heat energy emitted by a body from higher temperature to lower temperature is only because of movement of electromagnetic waves due to change in electronic configuration of the constituent atoms or the molecules of the body. The energy emitted per unit area as the thermal radiations is called emissive power of the body. Here, the maximum energy that can be emitted by the radiation process is given by the Stefan-Boltzmann's law, which is expressed as EB equal to, that means total energy the transferred is equal to sigma into A into T to the power of 4 now, where EB is equal to thermal energy that is transmitted per unit time, T is equal to area of the surface, which is expressed in a meter square, and T is the absolute temperature, which is measured in degree of Kelvin, and sigma is equal to Stefan-Boltzmann constant. This value is equal to 5.67 into 10 to the power of minus 8 W per meter square per degree Kelvin. These are the three modes of heat transfer that is taking place between the two bodies or regions. Now we are discussing now, concentrating on radiation by heat transfer. That is heat transfer by the radiation process. Already I told, we discussed the energy is transferred between the two regions which are far away from each other, not having any physical contact. That process is called radiation process. In this case, the medium is not required. That means without aid of any intervening medium, and the radiation is taking place because of electromagnetic waves now. So the radiation is found to travel at the speed of light in a vacuum. The speed of the radiation is equal to 3 into 10 to the power of 8 meters per seconds. The term electromagnetic radiations encompasses many types of radiations, namely the short wave radiations such as gamma, X-ray, microwave, and long wave radiation like radio wave and thermal radiations. The thermal radiations emitted in the range of wavelengths approximately from 0 to 0.1 to this 100 microns in the black body. Generally, the black body does not exist in the nature, but the ideal black body is the body which absorbs all the radiations which are incident upon it at any wavelength as well as the temperature. When it is observing all the radiations at every wavelength as well as the temperature, that means it is also emits the same magnitude of heat energy from its surface now. That means the amount of its observation is always proportional to the amount of energy that is emitting now. So black body radiations, the radiant energy emissions per unit area per unit time from black body over all wavelength is defined as the total emissive power. It is denoted by capital E beam. The radiant energy emission at a given wavelength, that is lambda, is known as monochromatic emissive power, and it is represented by E B gamma. The monochromatic emissive power at a given wavelength and at a given temperature is given by the equations, that is here E B delta at a given temperature T, it is equal to C1 divided by delta 5 into e to the power of CT2 divided by gamma minus 1, where this EBY at T is representing monochromatic emissive power at a given level lambda and a given temperature T. Generally, it is expressed in watts per meter square per meter length, where lambda is representing the wavelength. Generally, it is expressed in meters. C1 and C2 are the first radiation constant and the second radiation constant. These values are 3.7415 into 10 to the power of minus 6 watts meters, and second one equal to 1.4388 to the power of minus 2 meter degree Kelvin. Black body emissive power. That is, emissive power is the amount of energy that is emitted from the black body is known as air emissive power. Here, according to the Stefan-Boltzmann equation for the black body, the emissive power is given by EB equal to sigma into T to the power of 4 now, where sigma is the constant. Its value is equal to 5.67 into 10 to the power of minus watts per meter square per K to the power of 4, that is degree K to the power of 4 in SI units. And EB is representing the total emissive power. Generally, it is expressed in watts per meter square, and T is representing absolute temperature, which is measured in degree Kelvin. The integral equation is given by which leads the Boltzmann constant, which is expressed as EB is equal to the integration from 0 to 2 E B delta into d delta. This is the integral equation for the Stefan-Boltzmann equations. The another use of the relationship is the determination of radiant energy emission in a given wavelength delta 1 and delta 2. The two are given. This obtained by using equations within the limits delta 1 and delta 2, which is given by EB is equal to 0 to delta 2 EBY d delta minus 0 to delta 1 EBY d delta. That means the emissive power obtained between delta 1 delta 2 is equal to the emission power that is obtained from 0 to delta 2 and the emissive power obtained from 0 to delta 1. This difference is giving the net heat energy, that is emissive power emitted by the given object. So the equation can be modified as EB is equal to the integration from the limits delta 1 to delta 2 EBY into d delta. The radiation properties. The radiant energy incident on a body may be generally classified into three ways now. The part of the energy may be absorbed, part of the energy may be reflected, the remaining part may be transmitted. That is, when the energy is nothing but incident on any body, we cannot use the words that entire energy is absorbed by that body. If it is absorbed, then the type of body is called black body. But here, in universe generally, the perfect black body will not exist. Hence, the bodies, depending on the characteristics, some bodies may be absorbed that energy which is falling on it now, or some part it may be reflected, some part it may be transmitted from other surfaces or other objects. Okay, the fraction of incident radiant energy, that is the observed energy of the body, is called observability of the surface. That means here the observability means the amount of energy that is observed by the body to the total energy that is incident on the body. It is called observability. Generally, it is expressed or represented by using gamma. It is alpha. The fraction reflected is called reflectivity. It is represented rho. That means the reflectivity is defined as the ratio of the fraction of heat energy that is reflected to the total energy that is incident on that surface or on the body. The third one is the transmitted. The transmissivity is defined as it is a fraction of heat energy that is transmitted to the total energy incident on that surface. So when we are now adding alpha plus gamma plus tau, that is the transmissivity, is representing the total energy that is incident on the body. Hence, alpha plus gamma plus tau is equal to 1. These properties at a particular wavelength is called monochromatic properties. That means these are abbreviated as delta, gamma, rho gamma and tau gamma. That is nothing but the particular wavelength, that is the amount of observability or reflectivity transmitted at a particular wavelength is given. These are treated as monochromatic properties. General application of total properties are used generally. However, for special applications, monochrome properties are used now. Hence, the conclusion from the observability, transmissivity and reflectivity, the sum of alpha plus gamma plus tau is equal to 1 represented. For oblique surfaces, that means nothing but here that transmissivity is 0, which is equal to alpha plus rho should be equal to 1. This is known as oblique surfaces. For the block body means the entire energy is absorbed by the body, hence it is not at all having the property of transmissivity as well as the, hence alpha is equal to 1. That the emission is also 0. That is here now reflectivity as well as the transmissivity both are not at all applicable for the black bodies, hence alpha is equal to 1. The Kirchhoff's law, that is important relations for the black body, which give the relationship between the emissivity and absorptivity, was postulated by Kirchhoff. According to this law, the observability of the surface at a given temperature and wavelength is equal to the emissivity of the surface at the same temperature and wavelength. For particular applications, the sensitivity is simplified as epsilon is equal to alpha. That is, the observability is equal to emissivity. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.